Welcome to Structural MD episode 005, Robotic Arc Welding for Additive Manufacturing. I'm your host, James Hilgus. This episode has a special place in my heart simply because this is what I always envisioned. Before I knew anything about 3D printing or did any research into 3D printing, this was the process that I had in my mind that would work for construction. And that's not to say that I knew everything or had all the answers, but this is just kind of what I saw in my mind and I saw at Edison Welding Institute down in Columbus, Ohio when I took a tour. The reason being is because a lot of the other metal printing processes have a small build volume, which really doesn't make them applicable to civil engineering. In addition, those processes typically deal with more expensive materials like titanium, and titanium doesn't see too much involvement in the civil engineering or construction industries, whereas with wire-fed additive manufacturing or any welding process, as we'll touch on later, can deal with a wide variety of alloys, not just the more expensive materials. The build volume is a lot more unlimited, if you will, and has the potential to grow, and I will touch on that later. But right now, for the time being, there's one thing kind of holding back the technology from reaching a larger scale application, which I will touch on. And the show notes can be found at structural-md.com/P005. There will be the show notes and any links mentioned, and also videos will be there as well. Let's jump into the basics. Wire-fed additive manufacturing is divided into three groups depending on what is used as the energy source, whether it's a laser, it's arc welding, or an electron beam. Like I mentioned earlier, these wire-fed processes of additive manufacturing are a cousin to the powder-fed or powder bed technology. Just instead of the material being in a powder form, it's in a wire form. Wire being a tad bit cheaper, as I'll touch on the pros and cons, simply because the powder has to undergo additional processes to get it into that raw material form. Robotic arc welding has been around in manufacturing for a long time, just being used simply to join pieces of metal together or perform welds at a quicker pace than a human and more precise. However, recently it's been used for additive purposes in addition to simply welding. And yes, we can split hairs and say that welding is an additive process, but additive in the sense that you are building up a part versus just joining two pieces of metal together. This process is preferred to the manually applied semi-automatic gas metal arc welding simply because of the higher deposition and higher travel speed rates, which increase productivity at the end of the day. It is similar to other processes. On the micro level, it's bead by bead. But if you zoom out a little bit and look at the macro, it goes still layer by layer by layer. A couple things that you need to consider, though, when using this process is because it's basically like welding, you must consider induced distortion when designing parts. Warping that can occur from the heat being applied in different areas at different times and the cooling rates of that. The big bonus of using robotic arc welding is its deposition rate. You can get typically around 5 to 10 pounds of material per hour, and this can be increased with additional robots. So that's 5 to 10 pounds per hour per robot, and if you use more than one robot on a build, you can get an increased deposition rate. However, like I mentioned on the induced distortion via the welding process, you also should probably have an in-depth understanding of arc dynamics, weld puddle fluid flow, and weld bead stacking techniques before really diving into robotic arc welding. So how does robotic arc welding work? Let's take a look at the tools. If we zoom out to the macro level and look at the overall system, there's really three main components. There's the teach pendant, which is simply the controller that you see. It looks like a giant keyboard, if you will. If you've ever seen an overhead crane, most of them have a teach pendant somewhere. A lot of them are obviously becoming wireless, but a lot of the older ones have a cord that is connected to the motor control. So there's a teach pendant, a welding torch and robot arm, and then the metal inert gas and welding power source. So there's three main components, but if we zoom into the micro and look at just the welding system itself, There's a power source where the welding current is generated, and then there's a wire feeder which pushes the wire through the welding gun. This can be a separate unit, or it can be inside of the power supply to make things more compact, and typically they are inside of the power supply. And then obviously there is the welding gun, which in our case is being held by the robot, or typically it's also held by a human in obviously non-robotic form. Wouldn't you know that? So the steps are very similar in each process. First, starting off with the robot path and welding process. Next, you're going to do a selection of welding parameters. This is going to be controlled based on what you are building and the material that you are using. Things like thickness and geometry and orientation. Next, you're going to set up the weld path programming. Typically then next, before you start quote unquote wasting material or using material, you'll do a test of the program setup to make sure that things go smoothly, the robot doesn't freak out, and it understands the language or code that you're giving it to do. Step 5 is simply execute the weld, and step 6 is the end result. Now, the one thing that is holding this back, and if you noticed it, I said it in step 3, which was the weld path programming. Currently, we don't have CAD to part. Whereas with a lot of the other 3D printing processes, and there's still several more to come in the next episodes, you can pretty much go from CAD to part. Yes, you have to convert it to different file formats for the printer, but for the most part, it is simply going CAD to part. Whereas with this process, because it was originally used for something else, and we have tweaked it to serve our purposes in additive manufacturing, CAD to part technology isn't there, and this is definitely one of the bigger roadblocks, simply because there's a lot of additional steps like programming that have to go in before you can get your part, which adds time, and that defeats the benefit of additive manufacturing, or one of the benefits of additive manufacturing, which is the increased or reduced is a better word there, reduced product development time or product delivery time, where now having to go in and program for each part you make, that eats up that time that you would be gaining by not having to create molds or forms or other things of that nature that you gain by using additive manufacturing. So if we want to look a little bit deeper at the whole welding process, when the trigger is pulled on the wired feed gun, several things occur. First, circuits in the power source make currents available to the wire. A solenoid will then open a valve that allows the shielding gas to flow. The shielding gas will vary depending, again, on the welding parameters that you set. And then the drive rolls will feed wire through the gun. As the wire touches the metal, the arc is created and a weld puddle is started. You're able to control the wire speed and heat applied. And again, this is used based on what you are welding or the thicknesses of the materials you're welding. And there are different settings, and the very descriptive details of these different settings can be found in the show notes, but I'll just touch on the 3 different ones here. They are short circuit transfer, globular transfer, and spray transfer. I will also link up several videos that shows these on a very cool and slow motion level for your understanding. By no means am I a welding expert, so I myself don't fully understand them, but they're there at the show notes, which is again at structural-md.com/P005. The materials are basically any typical welding material: nickel alloy, aluminum, titanium, and steel. Basically, if you can get it in welding wire, chances are you can use it for robotic arc welding for additive purposes. The pros and cons, let's take a look at the bright side first here. Looking at the positive thing is always the best way to look at it. Like I mentioned earlier, the higher deposition rates is a huge benefit. It is much faster than powder bed processes. This can also be improved basically infinitely. Theoretically, it can be increased at an infinite rate just by adding more and more robots. Obviously, there's a law of diminishing returns, whereas if you add too many robots, the programming gets convoluted because you don't want the robots to collide with each other. But in a theoretical sense, you can always increase the deposition rate. Likewise, you can always increase the build volume by moving the robots around and essentially setting up to a freeform fabrication technique, which really opens up the build volume to as big as you can make the robots spread apart. Because of that build volume, this is more ideal for mid to large size components. The nice thing is with this process is you really get efficient material usage, so it's really green, environmentally friendly, which is something that's becoming bigger and bigger of an issue as we move forward throughout the years, which it's not 100% perfect, and nothing will ever be 100% perfect. That's physically impossible, but it's definitely approaching that range. Because robotic arc welding has been around for so long in manufacturing, there's a ubiquitous supply chain of parts, and it's relatively cheap to get into. It doesn't cost a whole ton of money compared to other industrial processes. And the last nice thing is there isn't a lot of post-processing that needs to go on, so you don't need to buy a ton of excess machining to do that machining of the parts. You get it down to the net shape that you want, so you can almost get a near net shape print. However, there is one big downfall that we'll touch on in the cons, and that is poor surface finish because of the stair-stepping effect. So because it goes bead by bead, layer by layer, you can really see the different layers that show up in the prints. And I'll put a picture of a print within the show notes, and it's just not aesthetically pleasing to the eye. And because of this, you can't really get a high degree of accuracy because of that stair-stepping effect. And the other con that I touched on earlier was the fact that we are unable to go from CAD to part. However, that I know is currently being addressed. There's a research paper that I wanted to access. However, the internet told me it was in embargo until July of 2017. So I will go back and take a look at that when that gets out of the embargo. However, I have reached out to the research team to see if I can get a hold of that paper. I know they charge $40-ish for it on the interwebs, and me being a college student, I don't want to pay $40, so I will take the chance that they will give it to me being a college student, and I will update you if I do get a hold of that. So in the additive slices section, I'm just going to touch on a few things that will be huge to push this technology forward. And the one thing is the increased ability to control the residual stresses and distortions in a large scale wire feed additive manufacturing. So like I touched on, the induced distortion because of you're using an arc welding as the heat source, that's something that needs to be considered, especially as the parts grow. Because right now, typically arc welding is used, you just do a bead or a weld bead down a line or maybe a couple, but it's not on a large scale where you're building up parts time and time again, especially on a very large scale. So all that heat leaving is something that needs to be looked at. Because this is a relatively new application of robotic arc welding, future development of wire-fed additive manufacturing issues with material quality, improvements in design for additive, increased capacity of monitoring and process control, and the introduction of more effective milling strategies needs to be investigated, as well as higher deposition technology to be able to produce full structures, which it's just not there yet. The goal is to be able to print a whole plane someday in the future. Not sure when that will be, but that is definitely something I'm looking towards. However, not an airplane, just more towards the civil engineering application and realm, and we will see where that takes us in the future. But definitely a technology to keep your eye on, especially if you're involved in the civil engineering or construction industries, as we may be getting parts eventually from a 3D printed process like this. So if you are involved in civil engineering or you know of someone involved in those industries, please pass this episode along to them just so they're even aware of the technology. It's a short episode, just about 15 minutes, and it'll definitely benefit them, if not today, definitely in the future, because 3D printing isn't getting any smaller. It's only seen growth year over year, and improvements continue to be made, just like the internet. Remember, people said the internet was a fad, and look at where it is now, and it's only been roughly 20 years. 3D printing is very similar. If you found this episode helpful, please pass it on to a friend. I would greatly appreciate it. If you need anything or would like me to come speak to your organization, feel free to reach out to me. My email address will be in the show notes. I'm happy to answer any questions or do any requested episodes. I will do the research for you and publish those in order. Until next time, episode 006. Thank you for listening.